Welcome to this series of lectures on source coding. This is meant to be kind of a quick primer to the source coding component of information theory, and in this series of videos I will focus more on tools and techniques rather than giving in-depth proofs. But wherever possible, if a short proof is possible, if a short proof can be given, then I'll try to give that. So most of the topics that I will cover is based on this textbook by Thomas Cover and Joy Thomas. It's titled Elements of Information Theory. It's a sort of the Information Theory 101 textbook, and almost everything that I cover will come from here. But at the same time, I won't be starting from scratch. I'll assume some prerequisites, which are mainly basic probability to the extent of you should know, for example, what the weak law of large numbers is, and maybe some basic concentration inequalities like Markov and Chebyshev, and if possible Chernoff bounds. If you're not familiar with this, then you should go back to your probability textbook or lecture videos. The other prerequisite for this series of videos is essentially chapter 2 of Cover and Thomas, and this basically covers the definitions of entropy and information and basic properties like convexity, concavity. We won't use too much of these properties, but at least I will assume that you know, for example, the definitions of information, of mutual information and entropy, and basic concepts like chain rule and relationship between entropy and mutual information. Okay, so what do we understand by the problem of source coding? The problem of source coding basically deals with data compression. We have a file, and our goal is to compress it in the sense of saving space. So we have a file of maybe 10 megabytes. We want to bring it down to say 1 megabyte. But at the same time, we want to be able to recover the original file without any loss of information. And we typically do this on a day-to-day basis. For example, when we have zip files. So whenever we zip a file, we're compressing it essentially, and we can see significant space gains when we use say zip or gzip or 7z or any of the large number of compression algorithms available today. And in fact, whenever data is transmitted through a medium, for example, when you're transmitting files across a network, these are typically compressed and then sent. Of course, the kind of compression that is used there is different, and typically there are two different types of compression. Well, source coding is studied typically in two steps. One is lossless source coding, where you want to reconstruct the file without exactly, you don't want any distortion, any difference between the reconstructed file and the original file. And lossy source coding, also called rate distortion theory, where a small amount of distortion is tolerable. So the reconstructed file after decompression need not be exactly the same as the original file, and we're okay with if there is some small difference between the final file and the original file. And such lossy source coding, as the name suggests, does have a certain loss of information, since you're not able to reconstruct things exactly, but you're able to obtain better levels of compression. That is, you can compress it down to a smaller file size than what is achievable using lossless compression. At the same time, you can't reconstruct the file exactly, and you will have also seen lossy file compression in practice, and this is typically seen when you try to say save or modify images. So the JPEG format .jpg is a lossy compression format, Typically you have a raw file which is a very high quality image taken from using a high-end camera, and usually and typically when you convert the raw file to a JPEG file or a PNG file, there is some loss of information. If you try to zoom in, you'll see that the resolution is significantly worse than the raw file. Also, you would have seen this noticed it when, say, sending images for photographs over WhatsApp or some kind of social media site. Typically, the images that are transmitted across WhatsApp have a lower resolution than the file which is there on your cell phone, for example. And so basically what is happening is it's running a lossy compression algorithm. You're reducing the resolution, but at the same time you're also get a reduction in terms of file size. So the problem of source coding was formally initiated by Shannon in his 1948 paper, and basically that is what we will be following to in the next couple of videos. And then I'll switch gears and talk about what is called variable length source coding. So for the most part of this series of videos, I will only focus on lossless compression, and unless otherwise I mention it, I will be, whenever I mean compression, I will refer to lossless compression. So let's formalize these notions now. So what we start off with is a file xn. We assume that the file has n symbols. These may be n bytes or n characters. The exact contents of the file are not particularly important for our study. All we will mostly be interested in are the statistics of the file, and these statistics will determine the level of compression that we can achieve. So for our purposes, the raw file is going to be a set of n symbols, maybe n bytes or n bits, depending on what you take your alphabet to be. So each xi comes from, so this is an n length vector, so we'll model the original file as an n length vector, where each entry of this vector comes from some finite alphabet script x. So for example, if you're trying to compress a text file, each symbol xi could be an ASCII character, but on the other hand, you could also look at the file differently. If it contains only English words, then you could treat each symbol xi as an English word, as a valid English word, and separated by spaces perhaps. But again, the meaning of the file will not be particularly important to us, and that is the beauty of Shannon's theory. So, but what I would like to mention is that depending on how you choose your alphabet script x, so for example, even if you're trying to compress text files, you could treat this as a sequence of ASCII characters or a sequence of words, or even a sequence of sentences. Each alphabet is a sentence. So for example, for ASCII characters, the script x is the set of ASCII characters. For words, script x is the set of words in say the English dictionary, and if you treat each symbol as a sentence, then each script x is a valid sentence in English. But depending on how you model this, depending on how you choose your script x for the same file, you can get different levels of compression. So maybe treating it as an ASCII character will give you a certain level of compression, but treating it as words may get you a better level of compression. But anyway, we'll treat this in a very abstract form, and we'll see that this abstract form is pretty powerful because it allows you to disassociate the meaning of the file with certain statistical parameters, right? So we'll assume that the file is random and it comes from some distribution. In general, the distribution could be some joint distribution on xn, pxn. But for the most part, we'll assume that the sequence xn is going to be so xn, the vector xn consists of independent and identically distributed components, where each component is distributed according to px. So px is a probability mass function on script x, and xn is IID according to px. Right? And for at least for the first few videos, we'll assume that xn is IID, but later on we'll see what happens if xn is not IID. So the goal is to compress this file. So if you did not do any kind of compression, then it takes a certain file size, right? So the size of the file is something, and the goal is to bring down the file size. But even to introduce the notion of a file size, we need a standard measure. So here I've said that xn consists of n symbols, but what n is for a given, say, an English text file can depend on what you take script x to be. So for example, you have a certain file which has maybe 10 words, where each word is maybe 5 or 6 characters long. Now if you treat this as ASCII characters, then you would have around 50 to 60 characters. But then if you treat this as words, then the file will have 10 words, right? When I say file size, it will typically mean in binary. So if we had to represent all of these using binary symbols, if you want to represent xn using binary symbols without any loss at all, then how many bits would you need to represent the file size? If we know that all of these consists of n symbols, and each symbol comes from the alphabet script x, then you would need log of the size of the alphabet ceil. Right? So you need these many bits to represent the file without any loss, correct, if you wanted to reconstruct it. And this would generally be equal, so this would be equal to, so basically you need n times ceil of n times log of size of x, many bits, to represent the original file, right? So our goal is to represent this file using a fewer number of bits. So our goal is to design a pair of algorithms, a compressor and a decompressor. The compressor takes this file as input and outputs a binary file. It consists of k bits, and where this k is hopefully less than n times log size of x. But the parameter k can depend on n, it can depend on script x, it can depend on px, but in general it could also depend on the file itself, on the realization xn. So maybe for one file you can compress it down to 10 bytes. For another file you may have to, so maybe the compressed file is 100 bytes. And whenever you do zip or gzip or one of these lossless file compression formats, the file size is always different. For one text file, when you zip one text file, say a 1 megabyte text file, the compressed file could be 100 kilobytes, but then for another text file, it could take maybe 110 kilobytes, right? So k may or may not depend on xn, and based on this distinction, we categorize compression algorithms into two types. One are fixed length compression algorithms, where k is fixed. Irrespective of the realization of xn, k is always the same. We fix k beforehand. We know that we're going to get a file of size n, of size n symbols, and they come according to some statistics, and we want to represent it using k symbols, where k is fixed. On the other hand, you could let k depend on the actual realization of xn, and this is called variable length source coding. But ultimately, irrespective of how you get ck from xn and irrespective of what k depends on, our goal is to somehow reconstruct xn, right? So the decompressor is going to be an algorithm which takes as input ck, and possibly it could also take as input px. So both the compressor and decompressor may take as input px, but or sometimes it may not take as input. It may take nothing as input, but it could take px as input, and it outputs an estimate of the original file, which we call xn hat. And in lossless compression, we typically want xn hat to be equal to xn modulo a small technicality. So in fixed length source coding, k is fixed, and we define the so-called rate of the compression scheme to be equal to k over n. Since k is fixed, k over n is a fixed constant for a given set of parameters px, script x, and n. So this is called the rate of the compression scheme. But clearly, if k is strictly less than n times log of size of x, we will not be able to reconstruct every single file, right? Just by the pigeonhole principle. So we can't reconstruct it exactly, but we can reconstruct it with high probability. So our goal, so the quality of our compression algorithm, the quality of a fixed length compression algorithm is determined by this quantity, the probability of error, which is the probability where the probability is taken over xn of xn not being equal to xn hat. So we allow the decompressor to make an error, but the error happens only for certain files. So with very small probability, so you see a random file as the input to your compression algorithm, and the decompressor outputs xn hat. So xn hat must almost always be equal to xn, but sometimes it's allowed to make an error. And the probability that it makes an error is called the probability of error. And typically the goal will be to make this as small as possible. So this should be close to 0. On the other hand, when we discuss variable length compression algorithms, k can depend on n, but also on xn itself, the realization of the file, right? And the rate, or the expected rate, is defined as the expectation of the length of the compressed file. So here k is going to be a random variable depending on xn divided by n. Sometimes I'll call this expected length L of ck, which is k, but we'll also refer to this as L of xn, where L of xn is the length of the compressed file of xn divided by n. And here we always, in variable length compression, typically we'll want xn to be equal to xn hat for all xn hat. So there is absolutely no loss. We want exact reconstruction. So fixed length source coding is sometimes called almost lossless source coding, but variable length source coding is perfect, no loss, lossless source coding, right? So these are the goals of source coding, and typically we will be interested in a certain parameter regime. So our goal is to maintain, is to have R to be as small as possible, for fixed length source coding, we want PE to be as small as possible. But clearly there's a trade-off. If you want a very small probability of error, then the rate will have to be larger, and if you want a very small rate, then the probability of error will increase, right? So there's a very delicate trade-off, and we won't study this trade-off exactly. What we will be interested in instead is the large N regime. So the case n tends to infinity turns out to be slightly easier to analyze. So we want to know what is the rate, which is the limit as n tends to infinity of k over n. But at the same time, we also want that the limit as n tends to infinity of the probability of error is equal to 0. So for large n, we want the probability of error to be vanishingly small, but at the same time we want to minimize k over n to as much as possible, right? So this will be the setup for fixed length source coding. But for variable length source coding, we'll indeed look at very small n and find out what the fundamental limits are, right? So now let's take a brief look at fixed length source codes, and let's pose the source coding problem, the fixed length source coding problem, in the following. So what is the goal? We are given a set of so where we have xn. The goal is to come up with a ck. So we have k bits where k is fixed, and our goal is to have a probability of error as small as possible, right? PE small. Now if our goal is to minimize the probability of error and k is fixed, so these are all k length one. So these are all the k length binary sequences. You are allowed to optimize over all possible mappings. And if k is fixed, then what is the smallest probability of error that is possible, and what is the best compression algorithm that is possible, right? I suggest that you pause this video and think about it for a while regarding what is the best probability of error that you can have. The optimal source code in this case can be described explicitly, but yeah, just think about it. Okay, so it turns out, and it's pretty easy to convince yourself of this, that the optimal fixed length source code, which minimizes the probability of error for a given k, is the following. You write all possible binary strings over here in any arbitrary order, all binary code words of length k, and corresponding to each code word, you need to associate a sequence x1n, x2n, up to x2 to the k n. There are 2 to the k possible sequences. So, and of course there are many sequences which do not have code words, xn 2 to the k plus 1 up to x size of x to the n, right? So these are sequences which do not have any code words associated with them, and these are sequences which we are going to map to certain code words, right? So if you observe any of these sequences, then maybe the compressor will output the all ones sequence. Okay, but whenever the decompressor observes one of these sequences, one of these binary sequences, it is going to output the corresponding message over here. So these sequences are what we'll call messages, and these sequences are possible code words. Right? Okay. So these are going to be sort of the set of reconstructible messages. In the sense that the decompressor, sometimes called the decoder, will output one of these messages upon observing these sequences, but these are sequences which will never be outputted by the decoder. So whenever the compressor or whenever the actual source file is one of these sequences over here, you will be able to reconstruct it without error. But on the other hand, if you observe any one of these sequences, you will always be in error. So the probability of error, so let's call this, say, script n. So the probability of error, it's not hard to convince yourself, the probability of error is the probability that xn belongs to this set n of non-reconstructible sequences, right? Or in other words, this is equal to sum overall xn in n of pxn of xn, right? And in fact, any source code must operate, any fixed length source code must operate along in this mechanism itself. So every fixed length source code can be represented in terms of a reconstructible set and a non-reconstructible set. So if you want to minimize the probability of error, what should we do? We should minimize this particular probability, or in other words, the sequences in n should correspond to those sequences with the least probability, right? So a very easy approach or to construct an optimal fixed length source code is to write all possible sequences x1n, x2n up to x script xn. So you write all of this in the decreasing order of probability. So the probability of x1n is greater than or equal to the probability of x2n, and so on. And the sequences with the highest probability will be allotted these code words, and the sequences with the least probability will not be allotted a unique code word. So these sequences will be allotted unique code words, whereas these sequences will not be allotted unique code words. Right. And it's again not very difficult to see that this fixed length source code has the least probability of error. Why is that? Because if you exchange any two of these sequences, then the probability of error can only be higher, because the probability of this occurring will be less than or equal to the probability of this occurring. So this is an optimal fixed length source code, right? So although this is an optimal fixed length source code, does it mean that we've solved the problem of source compression? The answer is no, for two reasons. One, a purely theoretical reason, and the other is practical. So the purely theoretical reason is, although we know exactly what the best fixed length source code is, measuring the performance of this fixed length source code is a bit difficult. For example, I know that this is the best source code, but if you ask me what the rate of this source code is, I can't give you an answer immediately. It's hard. So that's sort of the theoretical problem, and we also have a practical problem. The practical problem is that for small n, it's great. You know exactly how to compress, how to decompress. So, and the compression algorithm basically consists of maintaining this table of sequences, reconstructible sequences, and code words, right? But on the other hand, for large n, this is very wasteful. You need to maintain an enormous table for each sequence, and both the compressor and the decompressor must look up this table whenever they want to compress or decompress. So this is heavily wasteful in terms of space, and this is not practical. So as soon as you change px, so if a different file has a different px, then you need to change the table entirely. So this is a very impractical compression algorithm. So in the next sequence of videos, we'll see certain near optimal compression algorithms. First, we'll see some fixed length compression algorithms, which are not practical, but we'll see that we can quantify the performance in terms of the rate. We can say exactly what rate it achieves, and we'll also give the fundamental limits of the rate. So what is the smallest rate that we can achieve for a vanishingly small probability of error? And once we have a good understanding of fixed length source codes, we'll then go into variable length source codes. And although the requirements are slightly different, it turns out that the fundamental limits turn out to be close, approximately the same.